Recently, a new class of AI has taken the tech world by storm: large reasoning models. These systems generate detailed, step-by-step thoughts before answering a prompt, giving the strong impression that they are genuinely reasoning through problems. But new research shatters the illusion of how smart these models actually are. These models routinely score at the top of advanced math and coding tests, but there is a hidden variable in those scores. Because these systems are trained on massive swaths of the internet, the benchmark test data is often already baked into their training. This brings up a concept researchers call stochastic parrots. Language models are essentially highly advanced string prediction engines. They excel at manipulating linguistic forms to output the right sequence of words, without possessing any natural language understanding of what those words mean or the logic behind them. So, if we rely entirely on contaminated tests, we might not be measuring an AI's capacity to think at all. We might just be measuring its memory. To find out what is actually happening under the hood, researchers from Apple completely stripped away the standard math tests. Instead, they built controlled, deterministic puzzle environments, like the classic Tower of Hanoi. These puzzles rely on strict physical rules rather than common web data. This allowed the researchers to precisely manipulate the difficulty of the problem by doing one simple thing: scaling up the number of pieces. They could observe exactly how the models reacted as the puzzles grew from a few disks to dozens. By removing the possibility of memorization, this experiment isolates pure algorithmic logic. It gives us a clear, uncontaminated window into how an AI behaves as a problem becomes more difficult. Results revealed 3 performance zones. In Zone 1, low complexity, standard models perform better and faster than reasoning models. Examining internal traces reveals an overthinking trap. Reasoning models find correct answers early, then drift off, wasting compute tokens on dead-end paths. However, as the number of disks or pieces increases, the standard models start to fail. We enter the second zone, medium complexity. Here, the reasoning models shine. Their chain of thought mechanism allows them to test and verify multiple paths, successfully navigating the longer compositional depth of the puzzles. In this sweet spot, they appear to display robust, highly capable logic. But then we hit the third zone, high complexity. This chart shows model accuracy on the Tower of Hanoi puzzle. As the number of disks moves past 5, performance across all reasoning models plunges dramatically, hitting absolute zero shortly after. This graph tracks the thinking tokens used. You'd expect an AI to spend more effort as puzzles get harder. Instead, the lines peak and drop. At a critical threshold, they output fewer tokens and fail despite having computing budget left. Providing the step-by-step solving algorithm made zero difference. Models collapsed at the exact same point, unable to follow explicit instructions. Furthermore, massive inconsistency exists across environments. Claude 3.7 flawlessly executes 100 moves on Tower of Hanoi, but fails after 4 steps in river crossing. Tower of Hanoi data is abundant online, while complex river crossing puzzles are rare. These bizarre, uneven breakdowns indicate that these systems are not deploying general logic. They are leaning heavily on fragmented, memorized data patterns. We are brought right back to the warning of the stochastic parrot. Despite the internal monologues and the impressive benchmark scores, the architecture is still performing highly sophisticated pattern matching, devoid of true comprehension. Grafting a thinking phase onto a language model creates a genuine advantage at moderate difficulty levels, but it does not grant the system pure problem-solving capabilities. It merely extends its range until it hits a strict mechanical limit. This matters immensely for how we deploy these tools. If we hand these models complex, multi-step planning tasks in professional environments, assuming they can independently reason through unexpected hurdles, we are inviting serious risk. Because until a system can consistently follow a basic set of provided instructions without losing its place or giving up, it does not possess generalizable reasoning. The computing power is staggering, and the text outputs are incredibly persuasive. But the thinking AI we see today remains exactly that: a remarkably convincing illusion.